All right, so here's an extra example from Beer-Johnston. This is, we call this base motion, and I'm afraid we're going to have to be a little adaptable with our subscripts. In the book, Beer-Johnston, they use lowercase m in the subscripts for multiple things, including the motion. It's really just meaning magnitude, right? So instead of using like capital letters or whatever for magnitudes, that's what they mean. So we have this sphere of 2 kilograms, and it's suspended by this massless rod. It's got a spring attached to it of 3.6 kilonewtons per meter, and it has a forcing base motion, right? So you can picture that the base of where the spring is attached is moving with a magnitude that goes back and forth of 3 millimeters and a forcing function omega f of 15 radians per second. And our mission is to try to find what the magnitude, the maximum velocity of the bar, angular velocity of the bar, and also find the magnitude of the maximum acceleration of the sphere, right? So A right here is for an angular velocity, and B is for an actual acceleration. So what we want to do, I'm going to go through the correct way. Sometimes I've been naughty and skipped this step. We want to establish the relationship between the weight of this bar, of the ball, excuse me, and the displacement. Because this is what they're showing up here, whether they've said it or not. I think they should have, or they implied it, I guess, that this is the equilibrium position shown, right? So that's horizontal before this thing moves. If this thing just stays where it is, it would be in this position. So in order to do that, the spring had to be compressed a little bit, the static deflection. To find that, you would have at equilibrium with the moment about A, we would get this relationship. And we don't need to go any further right here than to just leave it like that, because we'll make a free body diagram and an inertial body diagram for the part in an arbitrary displacement. Now, notably right here, this is probably the most important thing to look at when trying to mimic a problem like this, right? So let's do a little highlighting thing going on right here, is this guy down here at the bottom. And what's special about him is that it has 2 parts, or 3 parts really. He's got the motion that's taking place right here on the base times the spring, the static deflection times the spring, and then the deflection because the thing has moved a certain amount theta, and that's L over 2. And I'm just calling this whole dimension here L for the time being to keep it in variables. All right, so there's the thing, and then this is also showing it with a tangential. I didn't acceleration. I didn't bother to put the normal acceleration apparently in there. That would be ml theta dot squared. But because it goes through this point right here, when we take the sum of the moments, or for an arbitrary variable. Oh, by the way, we're also mentioning these are small angles. So the sine of theta turns into theta, the cosine of theta turns into 1. We take the sum of the moments about that A, and then it equals the sum of the effective inertial moments. So here you go. There's this the simple thing that we put it through. The only thing that we're going to note here is that if we rearrange this part of it right here goes to 0 because of this part right up there. Right, and I pointed this out before, but maybe not enough times that people get used to it. So there you go. So we have this form. All right, so there's the form we just looked at a second ago, and we can get it to switch it around so that the this part right over here is on the right hand side, and we get it into our typical form. Right, we can see something in front of theta double dot, something inside of theta, and then on the right hand side we have the sine. So we could use we know we have a non-homogeneous differential equation, so we need to plug in and get a particular solution. We know we're going to assume it's in the form of sine omega ft. So we'll say, and by the way, these are in thetas instead of x's as we've done before. So that's just really the big difference right here. Some magnitude of theta is what we have here, right? So this is a function of time, right? That theta is a function of time, whereas this theta m is a magnitude. And we take the derivative of it, take the second derivative of it, just like we did in the formulation of the original part, and we can plug them in, substitute them back into the original equation up above. And let's see, where do we, substitute this back into here. Right? Those thetas into there. And then we can also cross out all of the signs, just like we did before. Don't cross the L over 2's out. Although some of the L over 2's are going to cancel. So we get this, and we can now take that equation, which I've left back up right here at the top, and we can mess with it. We can see that we're going, if we want to solve for the magnitude of the angle, that we have this arrangement. There's some things that would cancel out, but I just left them in. And if we plug all of those things into place, we find out that that magnitude, like how much of an angle will this thing move up and down, is going to be 0.003 radians, right? And there's a bunch of trailing zeros to let us know that, hey, it came out to exactly that. So now if we want to answer this first part where we're asking about the magnitude of the velocity, angular velocity, the maximum angular velocity, we know that that'll take place when this equals to 1, right? So we just get 15, that's the force, the radians per second, times this, and we would get 0.4500 radians per second. And that's the answer for part A. And then for part B, we know that we would find that the tangential acceleration is going to be the length times theta double dot, and we could find that maximum is going to be L omega f squared times theta m, right? By the way, we got that from, we can get that back up from here, right? Boom, right up in there. That's the relationship of omega theta double dot. So we put them in there. 0.4 is the L, 15 squared times 0.3, and so now we get the acceleration of this piece. This is a demonstration, really, of just what's taking place, with the nature of the problem, and using differential equations along with dynamics to find the reaction to something for a given input. Remember, everything we're doing here is in the concept of, it's a box, this thing, we do something to it, what happens, right? And then so you can think of it as the magic box. In this case, we call this a white box as opposed to a black box. A black box uses data and then comes up with some magical thing it learns and says, if you give me an input, I'll get an output. A white box says, I'm going to use physics and figure out what the relationship from the input to the output is going to be. And I'm sure you really enjoyed this. So we'll do some more lecture coming up for now the damped frequency, damped forced behavior.